Morning. Welcome to Climate Change, Science Impacts, Politics, and Solutions. I'm glad you're here. In terms of speakers and lead instructors, Dana Nuccitelli, if you can stand. That's Dana. Dana's a great guy. He's very knowledgeable in climate change, physics, astrophysics. He's a special guy. He's got many peer-reviewed publications, and he also wrote a book on climatology versus pseudoscience. So he's the perfect guy to be running this course. He's from UC Davis Physics. He's got a master's there, bachelor's at Berkeley in astrophysics, and he's very active in contributing to the Guardian newspaper, the British newspaper Guardian. He's going to tell you a lot more about himself as he starts. I'm going to be lecturing today, but I'm also hopping a plane for Indonesia this afternoon, and Dana will be doing the next 4 or 5 lectures after this, and then I'll be back and we'll both be lecturing. And then the third person, Jim Lerner, he's from Stanford University. He's retired now also. He's a Renaissance member. And he got his degree in aeronautics and astrophysics, both his PhD at Stanford, his MS at Stanford, and his bachelor's at MIT in Boston. So you've got a good crowd here of people who are pretty familiar with the topic, and we hope to transfer some of our knowledge to all you folks. So without much ado,
Jim here?
Pardon?
Where's Jim?
Where's Jim? Jim is in Europe right now. So we're kind of globe-trotting all over the place, using all that, producing all that carbon dioxide in the planes. I'm sorry. You got to do it. There's all those bucket lists out there, and it takes a little CO2 to do that. This is a pretty timely day, as you probably all know. September 8th today, Saturday, is San Francisco. There's the Rise for Climate and Jobs Justice March. So they're expecting about 50,000 people to be marching for the climate today in San Francisco. That's a prelude to next week's meeting there on the Global Climate Summit that Jerry Brown has organized. And there's lots of events going on at that summit next week, the 12th to the 14th. Hundreds of different forums. There's going to be the official forum for scientists and politicians from around the world, and then lots of other ones. Look it up online. I'm going to bring this up again a little later. So that's the Global Climate Action Summit next week. So I think we can, I got a news feed this morning. These are the guys that are starting to march in the parade down in San Francisco. We can probably hit the lights now, I think. All right, how's that? Okay, from Vanuatu. They're involved with climate there as well because their islands are being flooded out and they have to move to other places, which when we get to that lecture, I'll tell you all about that. So what is climate change? Well, climate change is not a hoax perpetrated by the Chinese. It is not a scam by scientists to get more research funding. And it is certainly not fake news, despite what you may hear on the TV or the news. What we're experiencing is extreme variability that's going to be you for your lifetime, and we can expect unpredictable and extreme weather events. Actually, it's not expecting, we're experiencing those unpredictable and extreme weather events now, as you all have experienced. Now, as of 2018, scientists are publishing on the very extreme extremes, which we are now experiencing as well. So what's the difference between weather and climate? So this is a course about climate change, but it's also a course about weather. Weather is a short-term phenomenon. When you walk out of your house, you feel rain or sun or heat or hail. That's weather. It's the immediate environment that you face when you go into the environment. Climate is the long-term changes in the weather. So just be aware of those differences as we talk about this and as you communicate with other people about climate change. So, takeaway from this course is it's real, it's us, it's bad, but working together we can solve it. And we really can. If we have the right tools and the right motivation and the right political will, we can do that. So that's the course. Thanks very much. We'll see you. There are a couple details that we probably ought to cover. Okay, let's start with what is going on out there anyway. World is changing. Temperature is definitely going up. Rainfall is going up and sometimes it's going down depending on where you are in the country or in the world. Snowpack is going up or it's going down depending on what year it is. Fires definitely going up. Droughts up. Floods up. Sea level rise definitely up. El Nino events are going up. Seasonality unpredictable. Ocean productivity going down. I guess I should have had that arrow going down instead of up. I think we ought to start out on the same page, first of all. I'm sure that you've all had this information before in grammar school, high school, college, wherever you were. Everybody knows about the greenhouse effect, but I'm just going to start on the same foothold here. Start up here. The natural greenhouse effect is where the sun beats down on the earth. The earth absorbs some of that heat, and some of it is reflected back out into space. But there's these things called greenhouse gases, which are heat-trapping gases. And there's three of them that are really significant here. Carbon dioxide, CO2, N2O, nitrous oxide, and CH4, methane. Those are really the three big greenhouse gases. There's other ones too, but that we'll learn about later. So those are in the atmosphere, and they're trapping some of the heat. However, when the human-enhanced greenhouse effect is when those gases are produced in higher concentrations. So the same thing. Sun beats down on the earth absorbs some of that heat. A lot of it stays in the atmosphere. Some of it is reflected back out into space, but because of the increased CO2, increased methane, and increased nitrous oxide, those are holding and trapping more heat, so the earth heats up. That's the basis of it, not much more than that. And that atmospheric level is about at 7 miles. Scientists have known about this stuff and heat-trapping gases for a really long time. Joseph Fourier in the 1800s first understood that Earth's atmosphere retains heat. This is a long time ago. John Tyndall, an Englishman, 1862, discovered that water vapor and CO2 are the components that actually trap the heat. Svante Arrhenius, 1896, produced the first model of how CO2 warms the Earth. Now, he produced the first model. Clearly, there were no computers back then, but he used pencil and paper. 2 full years, day and night, he worked on that to produce this model, which turned out to be quite accurate. At the end of that 2 years, guess what happened? His wife left him. I don't know why, and I don't know what it says about us scientists, but he was definitely dedicated. He actually won the Nobel Prize, but not for this, but for something else. But he was a very bright guy. Guy Callendar, 1938, was the first to show that the Earth had actually warmed from increased CO2. And Charles Keeling, we're going to be talking a lot more about Charles. So let's move on from that. Oh, there was an article, just to show you again how early we've known about this. This is an article in a New Zealand paper in 1912, and I'll read it if you can't quite see it. The furnaces of the world are now burning about 2 billion tons of coal a year. When this is burned, uniting with oxygen, it adds about 7 billion tons of carbon dioxide into the atmosphere yearly. This tends to make the air a much more effective blanket for the Earth and to raise its temperature. The Earth may be considerable, this effect may be considerable in a few centuries. And here we are, we're seeing those effects right now. The first person that really blew the whistle on what's happening in terms of the global warming issues and made it more popular in terms of understanding and created a huge amount of controversy is James Hansen. He was the director of space studies at NASA. And here's a New York Times article in 1988 showing the figures that he showed in Congress that identified what was happening to our Earth. So, what's happening out there in the scientific world? Basically, 97% of the papers that took a position on human-caused global warming agree that, number one, it is happening, and number two, it's very largely human-caused. So there's a lot of information about this. Dana is going to give a whole lecture on the consensus project that produced this information. When we get all this information together, basically, I like to say that the scientists are the map makers, and you, the citizens and the policymakers, and I put policymakers in quotes right now, you guys are the navigators. So we produce the data, we give you the information, and you and the policymakers, the politicians and the people in Congress make the laws to protect us citizens and those people in the rest of the country and hopefully the rest of the earth. That produces something called science-based management. Hopefully, with the science, with the data, with the understanding, we can then create rules and laws that protect everyone from Armageddon later on. So what's happening to the different political entities within the country? The Yale Center for Climate Change Communication, the director, looks like it's cut off a little bit at the bottom, is Anthony Weiserowitz. And he's been doing a great job for the last decade or so, polling individuals, the different registered voters, on what they think about climate change. So bottom line, he's got liberal Democrats, moderate to conservative Democrats, liberal to moderate Republicans, and conservative Republicans. And those different colored lines represent how they've changed from 2008 to 2018 in terms of their views. So they've stayed pretty steady since that time, but now they're starting to increase. And so now a majority of registered voters think that global warming is caused mostly by human activities. Even some of these guys down here, the liberal to moderate Republicans, have reached over the 55% level, and they're coming on board to understand the facts. And as the scientists give them more facts, and as their houses are burning down and their houses are flooded away, they are starting to realize there's something to this stuff. So it's an interesting place to go online if you want to see it. It's the Yale Center for Climate Change Communication. So what kinds of tools do we use to investigate climate change? We have the modern evidence. We've been measuring global temperature and tidal, the ocean tidal gauges for the last 150 years or so, physically measuring them. We've been also physically measuring atmospheric carbon dioxide measurements since 1958, and we're going to look at that a little more closely here. And we've also been monitoring and documenting altered phenologies. Phenologies are biological processes and the timing of biological processes, like when does the first flower come out? What are the first budding? When do birds nest? When do they migrate? When do they breed? So these are all the same kinds of things that we call phenologies, and that happens with trees as well. So in addition to the stuff that we've actually measured and documented ourselves, there's also prehistoric evidence that we call proxies. And the proxies can bring us back in time a lot. So sometimes we use bat poop. That'll bring us back to what happened 1,200 years ago in these in caves where they have these piles of guano, and we can extract information about the temperature, the oxygen concentration, the CO2 concentration in some of those. Calcium carbonate or chalk from Roman aqueducts brings us back about 2,000 years. What was happening during that time when water was flowing through those aqueducts and this calcium carbonate built up on the aqueducts? That gives us more information. Tree ring data brings us back about 8,000 to 12,000 years ago in terms of understanding the Earth at that time. Ice core data will bring us back 100,000 to 800,000 years ago. Sediment core data, 55 million years, and oxygen isotopes in ocean animal shells, maybe back 65 million years. So there's a lot of proxies that we can use that are correlations to what was happening at those times way back when, before we were born. So what are these greenhouse gases that we just talked about? The primary greenhouse gas that we're going to be talking about and concerned about is carbon dioxide, CO2. That's about 82% of the greenhouse gases. Methane, which is CH4, carbon and hydrogen, four hydrogens, one carbon atom. That's 20 times more powerful than carbon dioxide. So it's methane is a concern, quite a concern. Even though it's about 20 times more powerful, it lasts much shorter time in the atmosphere. So methane lasts about 12 years in the atmosphere once it's released to the atmosphere. Carbon dioxide can last hundreds to thousands of years. So we're going to have a hard time getting that stuff out of the atmosphere or allowing it to deteriorate naturally. The next one that we had earlier was nitrous oxide, N2O. That's about 5% of the greenhouse gases. And then we've got a bunch of fluorinated gases that are about 3% of the total. So these are the main greenhouse gases that we should be concerned about. Okay, here's the big one, CO2, carbon dioxide. So we've got one atom of carbon right here, two atoms of oxygen make up carbon dioxide. It's a heat trapping gas, as we mentioned. You can't smell it, you can't feel it, you can't taste it, you don't know it's there until it does something mean and nasty like it's doing now. Where does CO2 come from? It comes from combustion of anything. Anything that's burning is producing CO2. And that's right now the main issues are fossil fuel burning from power plants, planes, trains, and automobiles. Remember that movie? All other kinds of combustion. You burn a tree, that's going to produce carbon dioxide. And surprisingly or interestingly, cement production produces a lot of carbon dioxide as well. It's about 6% of our CO2. So let's take a closer look at that. People, you are a respirer. So when you breathe out, what are you breathing out? Carbon dioxide. What are you breathing in? A lot of particulate pollution, but you're also breathing in oxygen and you're using it. So that's basically what's happening is people breathe out carbon dioxide. And the humans on the Earth probably produce about 2.9 billion tons of carbon dioxide a year. But careful, that's not a concern because actually originally our bodies and our tissues and all the stuff that we've eaten ultimately have come from either carnivores or herbivores or plants themselves, which have taken up the carbon dioxide out of the atmosphere. So actually it's a neutral process. They take it up, we eat it, we produce carbon dioxide, we're putting it back to where it came from. So humans breathing out carbon dioxide are not that big a problem, but if you could all hold your breath until the end of the class, we will be much better off because you'll be lowering the carbon dioxide concentration, okay? So where's the carbon dioxide coming from or going to? I'm disappointed that that's cut off again, but that's a equation for photosynthesis on the bottom. Basically, it says carbon dioxide plus some water in the presence of sunlight produces a long molecule called sugar or carbohydrate plus some oxygen. So plants are taking up the carbon dioxide that we and all the other power plants and everything else are producing. So, and also, there's the other greenhouse gas is methane. So many of you probably know that Bessie the cow and all the other Bessies out there are producing methane, a fair amount of methane actually. And those are, yep, you're right, they're cow farts. Cow farts are methane produced from Bessie. They produce carbon dioxide. And this clam down here, it's another example of a clam that's producing carbon dioxide, but also producing some methane too. Now, interestingly, most of the methane is not coming out of this end. 95% of it is coming out from the cow burping. So if you can, put a plug in the front end instead of the back end, you'd be better off. There's also other things that happen to come out the back end and hit the ground. They're also producing methane as well. So we need to get rid of all those cows. What's interesting is that we have 1.5 billion cattle on the earth, and each one of them produces about 25 to 100 gallons of methane per cow per day. That's a lot of methane. And that accounts for about 28% of all the methane emissions are these cattle, and that's about 3% of the total greenhouse gases that we have on the earth, which is fairly significant. Okay, here's the stuff that I want to talk to you about Charles Keeling, that guy we saw way back when. Charles Keeling was a fellow who in 1958, these are cut off again, that's a bummer. This is 1960 right here. So in 1958, Charles Keeling started measuring carbon dioxide at the Mauna Loa Observatory in Hawaii at 11,000 feet, volcano. And he did that all the way through the year. Every month he measured carbon dioxide, actually more often than that. But these red up and down lines here are annual lines of carbon dioxide up and down, up and down, up and down every time. The blue line is an average from from 1958 on to the present. And so we're going up here, all the way up to the top. And right now, we are at about, so you can see the line over here, 300, 300. We're now at 410 parts per million of oxygen in our atmosphere, as measured by Charles Keeling and his compatriots, his colleagues, at the Mauna Loa Observatory. So let's look at why that line goes up and down and up and down. If we look at the line down here, this is an annual cycle of carbon dioxide. So we start in January here, and then the carbon dioxide goes up and up and up in January until it reaches a point about April, March, April, May. What's happening in the springtime?
Photosynthesis.
Photosynthesis, very good. Okay, photosynthesis, the leaves are coming out in the trees. They're starting to absorb all that carbon dioxide, and they're literally sucking it out of the atmosphere. So his measurements actually showed very clearly that CO2 is being taken out of the atmosphere. It goes down, 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 down to September, October. What's happening in September, October? It's the fall. The leaves fall off the trees. We don't have that carbon dioxide being taken up anymore, and therefore it's going to start building up in the atmosphere again. Clearly, that's started to rise again up October, November, December, January, and we start all over again. So this is in the northern hemisphere. In the southern hemisphere, it's the opposite. So we understand that carbon dioxide is being taken out by the leaves. When the leaves stop, it's going to be building up again. That's why we have up and down lines throughout the year of the carbon dioxide concentrations. And we've passed 400 parts per million about a year ago. It's not a special number. It just means that it's increasing and increasing and increasing more. So this is that chart, that figure we just looked at. That was since 1958. And we're going to transpose that down here and look at the last 1,000 years of carbon dioxide in the atmosphere. And so it looks like this is the concentration, parts per million. So 280 parts per million, pretty steady over the last 1,000 years. Here was the Industrial Revolution, started in about 1750 or 1800, which then we started steam engines. We had to burn coal or some other fuel to produce this, this great revolution. And because we're burning all that fossil fuel, it produces carbon dioxide, which goes up into the atmosphere. And therefore, when we reach 1800, 1850, 1900, we then start, after the Industrial Revolution, when we're burning all this fossil fuel, we then start to see the carbon dioxide increase exponentially, all the way up, straight up on this scale, right up to the 410 parts per million where we are today. So let's look about even further than 1,000. Let's go back 400,000 years ago. And we see now concentration of carbon dioxide in the ice ages. So when we have less ice, the carbon dioxide is higher. When we have lower concentrations of carbon dioxide, we have ice building up into the ice ages. Glaciers form, continents freeze over, ice caps are very common. So we've gone down here about 150,000 years ago, coming out of an ice age, I'm sorry, going into an ice age, and then we're coming out right now. And here we are. Humans entered the scene about 200,000 years ago. And here's the Industrial Revolution right here. We've come out of the ice age, and now we're going up, up, up exponentially. Here we are now here. So we can see that after the Industrial Revolution, we're going way beyond anything that we've seen before. We're not going back into an ice age. In fact, we're doing just the opposite. We're going up exponentially higher and higher concentrations of carbon dioxide. So how do we assess what's happening with the climate and all of this stuff related to carbon dioxide in the atmosphere? The Intergovernmental Panel on Climate Change, abbreviated IPCC, which many of you have heard about before, produces these reports called assessment reports about every 5 to 7 years. And they've produced 1990, 95, 2001, 2007. The next one, and they produce a number of volumes typically. This one is the physical science, and the next one is impacts and adaptations. The next one is mitigation of climate change. And then there's always a synthesis report that the common layperson can read It's very informative, very interesting. We've got a lot of figures and graphs in there. The next one was AR6, the Assessment Report 6, was supposed to come out in 2018 this year, but it's been delayed, so it's now expected to come out in the year 2022. So we'll be waiting for that, especially because of all of what's happening in the atmosphere. It's much more complex. The models don't exactly fit, so they're needing to do a little more research. Interestingly, this last November, a few months ago, or almost a year ago now, the U.S. Global Change Research Program, which is a combined effort of many different federal agencies and departments, came out with climate science special report, and it was basically overseen by the Executive Office of the President. And interestingly, this is the current administration, the conclusion of this report in November was in fact that number one, climate change is real, and number two, it's human caused. So interesting how that got approved through the president's office, but I guess not based on the information in the news recently about what's signed and what's not signed. I think you can probably understand how it got signed. Okay, let's move on beyond that. So the global community, the whole Earth, has been emitting about 100 million tons of carbon dioxide each day into the atmosphere. 100 million tons of carbon dioxide. That's about 40 billion tons a year. That's a little bit more than I want to deal with. And in terms of the fossil fuels being coal, oil, and gas, those are the three main fossil fuels, they account for over 94% of the total carbon dioxide emissions from humans as follows. We've got coal at about 42% of the total, oil is contributing about 33%, and natural gas is contributing about 19%. And again, the cement plants, it's a little complex process in the story, but I'll just leave it the fact that they're producing about 6% of the greenhouse gases. And changes in land use, like when we deforest in the Amazon, if we deforest areas, take those trees away, they are not sucking up that carbon dioxide anymore. So you have that deficit there, and therefore that increases the carbon dioxide, or at least it doesn't take out the carbon dioxide, and that contributes about 9% to the total. So let's go back to the 1920s and 1930s. Oil and coal built this country. Absolutely, it was fantastic. We needed it, we did it. This is what Huntington Beach looked like in the 1920s. Imagine going to the beach. Long Beach, this is Long Beach. Amazing. There's just pumping oil out of the ground crazy every single day, every single year. You probably didn't see those pictures before, but they're pretty striking. U.S. coal mining employment from 1900 to 2016 reached a peak in the 1920s, like I just showed you, and then that continued to decline down. And here's the, from 2000, the year 2000 to the year 2015, coal, again, the coal use has been declining. Why is that? Well, basically there's production efficiency in terms of the coal mining industry. There's lower cost of natural gas, which is competing with coal. There's alternative renewable energy sources, which are coming up very quickly now, also being competitive. And there's also regulations to protect human health, which has now slowed down the coal industry. And what's interesting is that in California, we have 10 times more jobs, about 500,000 jobs in the alternative energy field than the entire US has in coal jobs, which is only about 51,000. So we're moving ahead more rapidly than the rest of the country, as California often does, but we're moving into the alternative energy regime very, very quickly, and that's a good thing. So let's look at the concentration of carbon dioxide in the atmosphere, which is this black line up here, starting in 1980, going up to the present day. It's just continuing to rise up and up and up and up. And those gray dots and the gray line is the amount that's contributed by fossil fuels. So 80 to 90% of the carbon dioxide that's in the atmosphere each year over a long period of time is being contributed by those fossil fuels, coal, oil, and gas. And one thing that if you read about carbon that's in the carbon dioxide versus carbon dioxide, sometimes this graph on the left is only carbon. But you need to understand that because there's one atom of carbon and two atoms of oxygen, it doesn't feel like that's very much, but in reality, if you get 100 billion tons of it, it's a lot, and it does have weight, it does have mass. So because of the two extra oxygen atoms, the 1 gigaton or 1 ton of carbon is equal to 3.7 tons of carbon dioxide. All right, it's just much heavier, it has much more mass. So if you see a graph, you want to make sure they're talking about carbon dioxide and not necessarily just the carbon part. So out of the 40 billion tons, a gigaton is a billion tons. So out of 40 billion tons or 40 gigatons, 35 of those billions are coming from fossil fuels. So let's look at the global carbon emissions. Who in the whole globe, in the whole world, is producing this stuff? So if we looked at it as of 2017 and look at it by country, here's 1960 versus 2017, and it looks like this is ROW is the rest of the world. So we're looking at the big producers here. Up until the year 2004, the United States, that little green one, was producing the most carbon emissions. As of about 2004, China came up and passed the United States out, and now China just is ramping up hugely in terms of the production of fossil fuel CO2. The United States is going down, China is going up. The EU, the European Union, is going down. India is still increasing as well. So that's how much by country, how much each country is producing. Let's look at by individual person. So if we look at per person or per capita emissions over the same time period, 1960 to 2015 or 17, the United States has always been overwhelmingly the largest producer by individual person per capita of any of the other countries. The European Union, this is the rest of the world. And here's China still coming up by person, but it's way lower than the United States. It's half of the United States, if not less. And then there's India. Why is it that China as a country is producing way more than the United States, double the United States, and yet it's producing only half by person?
Population.
Huge population, exactly right. And each one of those people, because they're so populous, each one of those contributes much smaller amount than people in the United States, which are much more both income and also consuming. Let's look at temperature. If we look at the temperature increasing over time from 1880, the beginning of the Industrial Revolution, on up through to the present, you can see it's starting to go exponential again. And this is the concentration of carbon dioxide alongside that graph to show you that it's increasing along with, temperature is increasing along with the carbon dioxide. The last time, and we're up at 410 parts per million now, the last time CO2 concentrations were this high, humans didn't even exist. That was about 800,000 to 20 million years ago. And global temperatures were substantially higher, and there was almost no ice on the planet. Give you an idea of what it was like at this concentration way back when. So how hot is hot? 10 hottest years globally. We're looking at 2014, 2017, 2015, 2016, and the 5 hottest years were all in the 2010s, and we're getting hotter virtually every year. That marks 40 straight years of above average global annual temperatures. And the odds of that happening randomly without global warming is like 1 in 27 million. Temperature records are being broken. This is last year, 117 in Las Vegas. Hundreds of records are being broken in different cities all around the country every year. Early summer of 2017 was the most intense heat wave ever recorded so early in the summer. And we've got different things happening because of this extreme weather process. We've got severe drought over in the west. We've got heat waves breaking records. We've got severe storms in the middle of the country, and we've got torrential rains with tornadoes over in the southeast, and we've got a tropical storm down here, Tropical Storm Cindy. Just so happens my wife's name is Cindy, so I know a lot about tropical storms, let me tell you. East Coast is going through off and on temperature extremes as well. Where is all this heat going? Well, the upper ocean is taking most of it. The ocean is consuming about 92% of all the heat on the Earth. And ice takes a little bit, the land takes a little bit, and the air takes very little. Okay, so you've probably seen this movie, The Groundhog Day. Only in America do we accept weather predictions from a rodent, but deny climate change evidence from scientists. I'm just going to show you a short video here of the changes in temperature on the Earth from the 1800s, the Industrial Revolution. The darker colors are cooler. The orange up to the red are hotter. And you can see that the temperature isn't the same all over the Earth. It's changing everywhere. And it's building up. The 1940s, 1950s. Sometimes you get cooling, sometimes you get warming. 1960s, 1970s, 1980s, getting warmer. 1990s, 2006. Where is it heated the most? In the Arctic, in the northern pole area. So that's why the North Pole is melting. We're going to have an open Northwest Passage here pretty soon. And all the way through, a lot of people are working now on what are the economic benefits of having transportation through the North Passage. So we're going to take a 15-minute break here in a second, but I just wanted to give you this little thing. Politicians discussing global warming. This is an article or a painting that came out just a year or so ago.